Returning from the Moon, the Artemis II crew will hit the Earth's atmosphere at Mach 32. At 11 kilometers per second, the capsule covers the distance from London to New York in under 9 minutes. This velocity compresses the atmospheric gases ahead of the craft so violently that the air transforms into a glowing plasma bubble. External temperatures spike to 2,800 degrees Celsius. This environment is half the temperature of the Sun's surface. It is the single most lethal physical crucible of the entire lunar mission. After the uncrewed Artemis I test flight, a physical audit of the capsule's exterior revealed a significant failure in the defense systems. The heat shield's ablative material is designed to char and flake away slowly. However, Artemis I suffered catastrophic structural loss. Rather than a controlled burn, the material experienced chunking. Unexpected structural fractures left pits and craters in the shield in over 100 distinct locations. Despite these results, NASA decided not to fix the design for the next flight. The Artemis II mission will use an identical heat shield, protecting 4 human lives with a system that has already demonstrated unpredictable behavior. This means the upcoming crew will descend into a 2,800-degree inferno, relying on a defense system that has already failed its most significant stress test. The Space Launch System is a vessel of extremes, over 300 feet tall, producing 8 million pounds of thrust using repurposed space shuttle main engines. Yet, during re-entry, survival depends on the physics of a microscopic cross-section of material. Inside the Orion's ablative material, engineers discovered a bubble mystery. During the manufacturing process, microscopic pockets of gas can become trapped within the solid layers of the shield. As the capsule hits the atmosphere, the external thermal load transfers into the shield. Those trapped gas pockets absorb the heat and expand rapidly, generating massive internal pressure against the surrounding material. This pressure turns the gas pockets into micro-explosives. They detonate from the inside out, blowing away entire chunks of the protective surface and exposing the structure beneath to the plasma. The greatest threat to the mission is this invisible microscopic flaw, acting as a thermal detonator during the most dangerous phase of flight. Because the hardware remains unfixed, NASA's engineers are forced to mitigate this physical failure using pure orbital mathematics. During Artemis I, NASA used a skip re-entry. The capsule dipped into the atmosphere to slow down, bounced back out into the vacuum briefly, and then made a final descent. That bounce created a thermal soak period. It gave the trapped gas bubbles time to absorb heat and reach their explosive limit before the capsule reached the denser layers of air. For Artemis II, NASA is abandoning the skip. The crew will perform a single, continuous, steep plunge. The goal is to finish the descent so quickly that the gas bubbles never have enough time to reach the temperatures required to explode. NASA is betting that a faster, more aggressive mathematical trajectory can beat the chemical clock of the shield's internal failure. Grounded, this mathematical workaround is what stands between the atmosphere and astronauts like Christina Koch. The Artemis program is a legacy of high-stakes compromises. It relies on the Orion capsule, a design from 2012, launched by a rocket shoehorned into existence using shuttle-era boosters to satisfy congressional job mandates. These 4 astronauts will travel 400,000 kilometers from Earth, reaching the far side of the Moon before trusting this retrofitted architecture to bring them home. This danger is not for a sightseeing tour. It is the mandatory stress test required for deep space survival. Surviving this 3,000-degree gamble is the absolute prerequisite if humanity is ever going to move past low Earth orbit and permanently inhabit the Moon and Mars.